Have you ever wondered what happens when a massive star reaches the end of its life? This is where the incredible journey of neutron stars begins. Neutron stars are cosmic marvels, born from the explosive deaths of massive stars. In just a fraction of a second, a massive star collapses, giving rise to a neutron star. These dense remnants pack a mass greater than our Sun into a sphere the size of a city. Their extreme density creates gravitational forces millions of times stronger than what we experience on Earth. Neutron stars also spin incredibly fast, emitting beams of radiation that we detect as pulsars. Join us on a journey to explore the wonders of neutron stars, where extreme physics meets cosmic beauty. Stay tuned as we dive deeper into the mysteries of these celestial objects. Don't forget to subscribe to our channel and hit the like button for more fascinating space content. Neutron stars are among the most fascinating and enigmatic celestial objects in the universe. Born from the dramatic death throes of massive stars, these dense remnants pack an incredible amount of mass into a tiny volume, resulting in mind-boggling physical properties that defy our everyday understanding of matter and gravity. In this video, we'll delve into the captivating world of neutron stars, exploring their formation, characteristics, and the profound insights they offer into the nature of our cosmos. First, let's talk about formation process. Neutron stars are formed during supernova explosions, which occur when massive stars reach the end of their life cycle. When such a star exhausts its nuclear fuel, its core collapses under its own gravity, leading to a cataclysmic explosion. The intense pressure and temperature generated during this event cause protons and electrons to merge, forming neutrons and resulting in the creation of a neutron star. Now, let's talk about characteristics. Number 1, incredible density. Neutron stars are incredibly dense, with a mass greater than that of the Sun. Squeezed into a sphere just a few kilometers in diameter, this density gives them gravitational forces that can be millions of times stronger than Earth's gravity. Number 2, rapid rotation. Due to the conservation of angular momentum during their formation, neutron stars often spin rapidly, sometimes completing hundreds of rotations per second. These rapid spins result in the emission of powerful beams of radiation, which can be observed as pulsars from Earth. Number 3, exotic states of matter. The extreme conditions within neutron stars give rise to exotic states of matter, such as neutron degeneracy and quark matter, providing valuable insights into fundamental physics. After we have some information about neutron stars, let's talk about importance in astrophysics. One of the key reasons why neutron stars are vital in astrophysics is their role in studying stellar evolution. As the endpoint of stellar evolution for most massive stars, neutron stars provide insights into the processes that govern the life cycles of stars. Their formation during supernova events represents a critical phase in the dispersal of heavy elements and the enrichment of interstellar space, contributing to the chemical evolution of galaxies. Moreover, neutron stars are natural laboratories for testing fundamental physics theories. The conditions within neutron stars, such as intense magnetic fields and extreme pressures, allow scientists to explore phenomena like nuclear matter at densities far beyond those achievable in laboratories on Earth. Understanding the behavior of matter under such extreme conditions is essential for advancing our knowledge of fundamental particles and forces. Neutron stars also serve as cosmic beacons, emitting radiation across the electromagnetic spectrum. Their emission of radio waves, X-rays, and gamma rays provides valuable information about their properties, such as their rotation rates, magnetic fields, and emission mechanisms. Studying neutron stars across different wavelengths helps astronomers unravel the complex physics governing these exotic objects. Furthermore, neutron stars are integral to the study of gravitational waves. When neutron stars orbit each other or are in close proximity, they can emit gravitational waves, ripples in space-time, predicted by Einstein's general theory of relativity. Detecting these gravitational waves with instruments like LIGO and Virgo not only confirms Einstein's theory, but also offers insights into the dynamics of neutron star binaries and the nature of gravity itself. In summary, neutron stars are indispensable in astrophysics due to their role in stellar evolution, their significance in testing fundamental physics, their emission properties across the electromagnetic spectrum, and their contribution to gravitational wave astronomy. Studying these cosmic objects continues to deepen our understanding of the universe and its underlying physical laws. Neutron stars stand as cosmic marvels, offering profound insights into the nature of matter, gravity, and the universe's evolution. Their formation, characteristics, and significance in astrophysics make them captivating objects of study, pushing the boundaries of human knowledge and inspiring awe and wonder about the vastness and complexity of our cosmos. If you're finding value in this video, why not show your support by hitting that like button? It helps us know what content you enjoy the most. And while you're at it, consider subscribing to our channel. You'll stay updated with all the latest videos we release, ensuring you never miss out on new content. Plus, we love hearing from our viewers, so drop a comment below and let us know your thoughts. Your feedback is incredibly valuable to us, and we always appreciate hearing from you. Thank you for watching.